Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimum time to complete all the tasks. The problem states that there is a computer that can run an unlimited number of tasks at any given point. Now we are given some task. Each task is denoted by start, end and duration. It means that the task can be scheduled in any time between start and end, and it has to be scheduled for duration number of seconds, right? So let's say start and end is 2 and 5 and duration is 3. So it says that you have to schedule this task for 3 seconds anywhere between 2 and 5. Which one you pick doesn't matter, and that doesn't need to be continuous, right? So you can pick any 3 in between 2 and 5, and if that's the case, you can say that okay, task I is completed, right? So now we the computer has a special property. It says that computer needs to be turned on only when it needs to run a task, otherwise it can be turned off, right? Now we need to schedule this task in an optimal way such that computer is on for minimum duration, right? So that's what the problem is. Now let's try to take understand this with an example. Let's say these are the three tasks. Now this says that okay, first task can be scheduled anywhere between 2 and 3, and it has to be scheduled for 1 second. Similarly, third task can be scheduled anywhere between 1 and 5, and it has to be scheduled for 2 seconds. And this one also anywhere between 4 and 5, and it has to be scheduled for 1 second. Now one possible solution could be, let's turn on the computer at t equals to 2 and turn on the computer at t equals to 5, let's say, right? Now if you do this, you can see at t equals to 2 the computer can process task 3 and task 1. At t equals to 5 computer can process task 3 and task 2. Now task 1 is scheduled for 1 unit of time, right? Because at t equals to 2 computer is active, so this task is scheduled for 1 unit of time. Task 2 also is scheduled for 1 unit of time, right? And task 3 is scheduled for 2 units of time. Now you can see all the conditions satisfied. So task 1 is scheduled for 1 unit of time, task 2 is scheduled for 1 unit of time, and task 3 is scheduled for 2 units of time. So, and how many time computer needs to be turned on? Only 2 seconds. So that's where 2 is the answer. Now you can see, you can try any other possible combination and you will see you can't turn on computer for less than 2 seconds and still complete all the task. So that's where the answer here is 2, right? So hope the problem statement is clear. Now let's try to see how to solve this. Now what's the first, okay, so first of all, like what this picture is basically, it has four tasks. The first task is can be scheduled between anywhere between 0 and 4, and it has to be active for 4 seconds. Similarly, second task can be scheduled anywhere between 3 and 7, and it has to be active for 3 seconds, and so on and so forth. So now what's the first approach that should come to your mind? So basically you'll see the problem, okay, I need to maximize the utilization at every second, right? So let's try to fill, or let's try to turn on the computer when there is maximum overlap. So you will see okay, this point has maximum overlap, right? So let's try to turn on the computer at t equals to 3 and t equals to 4 together, like and you will see okay, these tasks are scheduled at these two instances, right? So far so good. Now let's say you can say okay, now what? So at t, you will say okay, now I am trying to see what are the overlaps. So what are the overlaps in which there, like what is the time at which there are two overlaps? So these are the three time instants where there are only two overlaps: t equals to 1, t equals to 2 and t equals to 5, right? Now which one of these will you pick first? That is something you will not be able to answer deterministically. So you can try yourself. Each, if you pick this one first, answer will be different. If you pick this one first, answer will be different. And if you pick this one first, answer will be different, right? So the thing is, because at there is a point, or there will be a point where you have to choose between equal probable instances, you don't want to just guess which one of, like, let's say you say, okay, I will take the first one. So there is no valid proof that you can come up with which say that, okay, if you pick the first one, you will be getting the best answer. So there is no valid proof of that, right? So that's where going greedily by only choosing the task which has, by only choosing the time instance which has maximum overlap would not work, right? So you can try that out yourself, like that the constraint is very small. uh, so you can just try this part yourself and you will see some of the test case failures, right? So going greedily by number of overlaps would not work. Now what's next? So why like number of overlaps doesn't work? Because we were looking across tasks, right? So let's try to look at only a single task. So let's say I looked at, let's say I try to fill only task 2, right? Now which one of these, we have to select three of them, right? Now which one will you pick? Again, you will try to pick the one which have maximum overlaps. So this has three overlap, right? This has three overlap, this has two overlap, and this has two overlap, right? So let's say here you say, okay, I will pick the one which, like, first of all, you pick this two, and from these two, like this has two overlap, this has two overlap, let's say you pick this one, right? Now as soon as you pick this one, again, there are two conditions, right? So you have to pick either this or this. So you can't deterministically say that you will pick this one. So let's say you somehow say that, okay, I will pick the first one, and that would be the best option, right? This would not be the best option. Why? Because let's say we complete this list. So we have these 3 points scheduled, like the computer is on at t equals to 3, t equals to 4, t equals to 5, right? Now we have scheduled 2 units of this task, we have scheduled 3 units of this task already, and with 3 units this task is complete, with 3 units this task is complete. Now 2 units of this task is left, so there is no overlap of this task with this task. So let's say you pick any two of them, let's say you pick this two, and for one, you let's say you pick this one. So how many times computer is active? 1, 2, 3, 4, 5, 6. So total 6 unit of time computer is active, right? But there is one possible configuration where computer would be active less than 6 unit of time. So let's say you pick, instead of this you pick this one, right? Now if you see, you will pick, let's say, this two as well, right? Now count 1, 2, 3, 4, and 5. Computer is active for 5, and you can see every task is completed. So basically choosing the first one would not work. Now you'll say, okay, choosing the last one will work. But you can come up with very similar test case where you will see, okay, choosing the first one would work. So basically every time you have options, you can't deterministically say which one to pick, and that's where this greedy approach would not work. Now where what to do now when any of these greedy approaches is not working? Now first, let's try to understand why it was not working, or like why picking this part was not giving us the correct answer. The actual reason here is we we picked this because we saw that, okay, these two are overlapping, right? That's where we picked this instead of this, right? But what happened was when we scheduled this 4, we have already scheduled 3 units of time for here. So this actually doesn't make any, like, this doesn't matter at all, because for this task 3 units are already scheduled, right? And because this didn't matter, this decision of selecting this one because it has two overlap actually doesn't make sense, because it only, though it has two overlaps, but because of this scheduling, it only has effective one overlap, like it doesn't contribute to anything else except this part, right? That's where this solution would fail. This solution failed. Now in other words, we can say that this solution failed because there were some task which ends before this task, and we were trying to finalize this task before finalizing the task which ends before this, right? Now, why that matters? Because if we would have finalized this task, we would already know that okay, every task that ends before me is already finalized. So whatever influence they can bring in any of the task is something that already happened, right? Now I can just pick the maximum overlaps, and that would give me the best possible answer, right? So again, I am repeating this part. This solution, the greedy solution that we have tried with by filling up this task first, second task first, failed because we choose this particular second because we saw that okay, there are two overlaps. But this two overlaps is actually not two overlaps, it is ineffective one overlap, because it doesn't matter whether you schedule task 3 at this time or not, because for task 3 all the three instances are already scheduled because we have to schedule task 1. So that's where we said that okay, this solution failed because we are trying to finalize a task which ends after a task which is not yet finalized. So we will always try to finalize the task which is first, like which ends first, and that's where the solution lies. So what we will do, we will try to finalize the task in the order of their ending index. So here we will finalize this task first, right? And then we will finalize this task, and then we will finalize this one, and finally we will finalize this one. So this is the order in which we will be iterating on. Now let's try to finalize this task. Now think about it. We have to select four indexes. Now, which one of these four indexes which you will you pick? The answer is you will always pick the last four. Now, why that's the case? The reason is simple. We know none of the task which ends before is there. Like this is like every task which ends before this task. So let's say there's a task like this, right? So this task is something which is already being finalized. So whatever effect that would have brought in this particular task is already taken care of. Now how that is taken care of, we will look at it. But for now, we know that this is the first task that ends here. There is no other task which ends before this, right? So there is no other task like this. So only task that can happen or that can overlap with this task looks something like this, right? Basically, it overlaps with some part and ends after this, right? So that's the only possibility. So because that's the only possibility, and we want to maximize the overlaps, we will always try to fill the last sections, right? Because that is the one which would be actually overlapping. Nothing else would overlap. So let's say we will fill some space here. So this space might be overlapping with one of these, but if it instead if we fill this space at the end, I am very sure that this space would overlap with the same task which might have overlapped if we have filled this space otherwise, right? So that's the basic intuition. Basically, every we are trying to fill the task because nothing ends before it, everything ends after it. So if we just fill the suffix, we know that that is the best we can do because we have filled some overlapping pieces already, right? So that's the entire approach. So here we have to fill four, so we will try to fill these four, right? Now once we have filled this, we will now go over and fill this part, right? Now here we have already filled this four, right? So this four are already filled. So we have to schedule this for 3 seconds only, and 4 seconds are already, like, computer is active for 4 seconds in this range. So you can schedule this task in any of these 4 seconds, and that would actually conclude this task. So there's no other action you need to take for this one. So now let's proceed to the third task. Now at this point, you know that this is scheduled and this is scheduled. So these two is something you will not take care of. So you know now this you have to just schedule for one more unit. Two units are already scheduled. Which one of these three would you pick? Again, we will try to pick the suffix part. Now, why suffix part? Because we know for the prefix part, everything should be taken care of already. We we only have task which now ends afterwards. Every task that ends before is something we have taken care of already. So we only have tasks which are end afterwards, right? And to actually overlap or a maximum overlap, to have maximum overlap, we will only filling suffix would suffice. So here we will again fill this part. Now once you fill this part is already filled, and now we will move to this task. And once you see there, like here one unit is already scheduled, so this task is all good, right? So that's the entire algorithm. Now just to reiterate what we have tried, we have seen that the greedy solution would not work because there will be a point where we have to make decision between two similar instances, right? Now that's where we find out why the greedy solution was not working, because in greedy solution we have some false news here. The false news is that it has two overlaps, like some time has two overlaps, but it may not have two overlaps because this task might have been already completed. Like whatever we have to schedule for this one might some is something which might have already been scheduled. So because of this false part, we need to avoid this false part as much as we can. So that's where we saw that this false comes because we are trying to finalize a task which comes after a task which is not yet finalized. So that's where we now are trying to finalize the task in the order of their ending index. Now once we have that part, that logic cleared, we now see, okay, what is the order in which we will try to finalize. Now once we have fixed this order, we will try to finalize each of these tasks one by one. Now for each of these tasks, one condition would be true. The condition is there is no task which will end before this. So there is no task like this or this, right? So there is no task that, because these two tasks would already be taken care of. So there is only task like this. Now because there is only task which have some suffixes, it is sufficed to only take or only fill the suffix part as much as we can. So that's where we will only fill the suffix part, or we will always try to fill the suffix part as much as we can. So we will start from the right and keep on filling it until we have um, some duration left for the given task. And we will just keep on applying this in the order of their ending index that we have decided on, right? So hope this entire solution makes sense. So the pseudo code would be very simple. It would look something like this. So we will just sort based on the r or the end index, and for each task we will first find out how much is already being used, or in other words, we already have filled all the prefixes, like we already have committed the timestamp for all the tasks which ends before me. So for all this task we will just try to calculate what all is filled. And if can use is sorry it should be greater than the duration. If can use is less than duration, then we will try to fill the indexes from the suffix, right? And finally after this entire loop ends, we will just go over is active array and count the number of indexes in which the CPU was active, and that will be our answer, right? So the time complexity, is we have tasks here, right? So this would contribute T, and for each task we are iterating over L to R, right? So this would contribute basically start minus end or end minus start, whatever you say, that basic the time range, right? And this part is again, in worst case it can go all the way up to L, right? So if we are starting from R, we can go all the way up to L. So this is again, this can go up to range. So the time complexity is T into R. So here T is 2000, R is also 2000, and that's where this would pass. Now, I would strongly encourage you to code the solution yourself. That would help you understand this problem a bit more clearly. And as a follow up, you can try to solve this problem in T log R or R log T. Like, I think both are achievable. I'm not sure about R log T very much. I haven't implemented that, but I think T log R is achievable. So you can try to solve that version of the problem in which, let's say R, like T is very huge, like it is not 2000, is 10 to the power 5, right? So that's where you will not be able to apply T cross R solution. So that's where T log R kind of solution would work. So I would encourage you to try that out yourself. That would not be as straightforward as this, but it would just include some sets or segment trees at the max. So you can just try that yourself. So let's look at the code. The code is simple. We sorted based on R. This is the comparator we have written, right? If RHS, like if R is not equal, we will just sort based on the R. Otherwise, we'll sort based on the L, right? Now after that, we iterated over all the tasks, right? Notice that this task is already sorted, so we are iterating in the sorted order, and we figured out what is the required duration for which this task needs to be active, and what is L and R. Now we go over all the index from L to R and see how much is active. So we'll just decrement our required. Now if required is greater than 0, it means we still have to schedule something. We will just start from R and go all the way up to L. So we will see if the current index is something which is not active. We will make the CPU active and decrement the required. And we will keep on doing this until required is greater than 0. So after this loop, we have filled all the suffixes. Like we have filled the suffixes which suffice the duration for this task. Now, after this entire loop ends, we will just iterate over all the uh, timestamps and see if CPU is active there. If it is active, we'll just increment the result and finally return the result as an answer, right? So hope the entire solution is clear. If you have any doubts in any of the section of the solution, please post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.